Today I'm going to be showing you a couple of examples of the Laplace transform being used to find the transfer function of a system. When we start to find the transfer function of a system, we follow a couple of steps. The first thing we need to do is to model the system with a differential equation, the same way we learned to do in the last unit of class. After we've found the system differential equation, the next thing we do is we take the Laplace transform. Once we have the Laplace transform, we're then going to convert the equation into the form of a transfer function. This step is as far as we're going to go for now, but I want to complete this series of steps so that you understand where it is that we're going with this. After we put into the form of a transfer function, the next step will be to multiply both sides of the equation by the Laplace transform of the input signal. Then, finally, we take the inverse Laplace of the transfer function. This gives us a final function in time describing what the output signal will look like. Before we move on and look at some examples, I just want to represent this 5-step process in the form of a flow chart. My hope is that this will clear some things up by showing you what form these equations are in before and after we complete this step. So we start out always with some kind of a physical system. This physical system might be a slinky, or a car, or a thermometer, or a box sliding across the floor, or a pendulum, or whatever it is that we want to model. The first thing we want to do to that physical system is model it in order to get the differential equations that represent the system. So the physical system goes through a process of analytical modeling in order to produce a differential equation. Remember that this differential equation can have 3 different kinds of things in it. It can have the input signal as a function of time. It can have the output signal also as a function of time, and it can have constants. Our goal here is to figure out what the output signal will look like given some specified input signal. So the differential equation, which is the output of the analytical modeling, next goes through the process of the Laplace transform. The Laplace transform takes in the input of a differential equation in time, and what it produces as its output is the transfer function. A transfer function is not a function of time, it's a function of s. And its format is the output as a function of s divided by the input as a function of s equals, on the right hand side we can have 2 kinds of things: constants and the variable s. Remember that our goal is to find what the output signal will look like over time given some input signal. So the next step that we do with this transfer function is we set a value or an equation for x of s, the input, some equation, and we multiply the transfer function by that input. What this produces out is the Laplace transform not of the transfer function, the whole system, but the Laplace transform just of the output. So here, we're only one step away from achieving our goal of finding the output signal as a function of time. The last thing we have to do is to take the inverse Laplace of the output equation. And the inverse Laplace converts this, which is a function of s, into the output as a function of time. So now we have a complete process that takes us from a physical system all the way to finding the output signal as a function of time.